day, I'm Dr. T, and welcome to my dining room table. So today I'd like to talk about molecules and really describing how we describe them more than just their simple chemical formula. So when we have molecules, these are going to be discrete clumps of atoms. They are going to typically be nonmetals, and nonmetals, like virtually always. Obviously there's always weird exceptions to everything. But yeah, and with these, they're not going to form lattices, at least not on the molecule scale. The molecules themselves might decide to crystallize into a lattice. That definitely does happen, but they're still discrete clumps. So in order to understand these discrete clumps, we need to actually look at the way in which they are bonded to each other, not just that they're all interconnected. We really want to see who is sharing electrons with whom, because these are covalent bonds. The way we do this is with Lewis structures. Now, there's actually two ways of doing Lewis structures. I'm going to show you a way that I prefer. It's not usually in most textbooks, though. It's kind of an odd choice. The way I prefer is going to start with the Lewis symbols, and then we're going to put those together. This works much better for large, complicated molecules that have atoms that do simple bonding. And this is going to be very much what we're going to see when we jump into organic and biochemistry. Fairly dull bonding. Carbon just bonds to four things. It's got a couple of choices, but that's about it. But really complicated patterns of them. The other approach starts out by counting valence electrons and then assigning them to atoms based on a series of priorities. This approach works much better for molecules that are made from a relatively small number of atoms, but have very complicated bonding patterns. Since in this course we're not really going to be dealing with those atoms much, instead I'm going to use the Lewis symbol starting approach because that is a better preparation for organic chemistry, which is covered in Survey 2. That said, your textbook will have the valence counting approach in it if you're interested to dive deep into that, as well as there are too many videos on the internet to shake a stick at. Okay, so making sure the camera is pointing at the paper. So let's start out, and I'm just going to do a couple molecules for examples. And the classic molecule I like to start out with is CH4. Now, this one you could call this carbon tetrite. I can't even pronounce it. Carbon tetrahydride, but no one does. This is called methane. This is going to be named based on the organic naming, and a lot of what we're going to be doing are going to be organic molecules that have carbon in the middle of them, because that's really where this shines and really where you get some much more interesting stuff going on, at least as far as complicated molecules. Weird bonding patterns, those are the metals. Those love weird bonding patterns. Okay, so to do this, what I'm going to do is I'm going to start out and I'm going to draw the Lewis symbols for each of my atoms. So I've got my carbon. I'm going to draw an invisible box. Actually, I'm going to draw it as a dotted line. Now, this invisible box for the Lewis symbol represents the s and 3p orbitals. There's no meaning as to which side. In reality, this would be a three-dimensional thing. It would be a tetrahedron. And those orbitals are going to start what we call hybridizing. They're not going to stay as an s and 3p's by themselves. They're going to start fusing together and forming different structures. The true s and p, d, f orbitals, etc. Really only hold true in the form that I described them in that video when the atom is completely by itself in a very thin gas or in a vacuum. This is not the case. It's going to be bonded to other atoms, so it's going to do different things with the electrons. Because they're electrons, they do what they want to do. Okay, now I have 4 valence electrons. I still have to count valence electrons. I have 4 valence electrons, and I know that because if I grab a periodic table, like this one, 1, 2, I skip the transition metals. And by the way, these are not going to, well, hydrogen's up there. Hydrogen is a weird one. He's kind of like both a metal and a non-metal. Obviously, the metals aren't going to be typically involved in molecules. I say typically. So valence shells going across the periodic table. 1, 2. The transition metals are doing something weird, so you skip the middle. Then 3, 4. Where at carbon, it's got 4 electrons in its valence shell, so we're going to put 4 dots. And we go ahead and we put 1 dot in each orbital by itself, And then if we've got enough to do pairs, then we start making pairs, but not until we've filled all 4. Okay, the other one I have is a hydrogen. Now, hydrogen only has an s orbital, so I'm simply going to draw a circle around the hydrogen because a one-sided shape is a circle. And on that one orbital, I put its 1 electron. It has 1 valence electron, it has just 1 electron period. Poor little guy. Okay, now what I'm going to do is take these Lewis symbols and I'm going to start putting them together. So I've got my carbon. I know I have 4 electrons, so I'm going to take one of my hydrogens and stick it over there. So now I'm going to have my hydrogen like this. I'm going to do another hydrogen. And remember, this is a circle. There's no meaning to which side is which. So I'm going to go ahead and put my hydrogen here. Then I've got a 4th one, or a 3rd one, and a 4th one. And actually, I'm done at this point, although typically there's another step to clean this up where I replace these pairs that are being shared. See how these two are essentially on the circle and the box? So I could draw an imaginary box that would be those same 4 orbitals and an imaginary circle for each of my hydrogens to represent its 1s orbital. And what it's showing is that those electrons are in both. And really what's happening is the orbitals are hybridizing together and becoming a new orbital that is around 2 centers instead of just 1. So then to clean this up, typically those pairs of electrons get replaced by lines, and the lines simply go between their constituents. Okay, so fairly straightforward. So let's go for another one because there's a couple of quirks that can still happen with this one. So let's go for formaldehyde. So formaldehyde is going to be a carbon, a pair of hydrogens, and an oxygen. Now, by the way, what I'm drawing are known as molecular formulas. They are going to be the formula for the entire molecule. These are not smallest whole number ratios, even though those both are, but they are in reality an actual count of every atom in the molecule. For molecules, we rarely use empirical formulas. Okay, so I'm going to draw my Lewis symbols. I've got a carbon, I've got a hydrogen, I've got an oxygen, and after a while, you just memorize these. Now, the hydrogen, once again, it's got the 1 orbital. So we draw an invisible circle. Normally, I don't draw this. I'm just doing this for show. Speaking of which, yeah, I think it shows up, I hope. Oxygen, like carbon, has in its valence shell an S and 3 P's, so I draw a 4-sided box. By the way, elements like sulfur and phosphorus quite often will have 6 or 5-sided boxes because they bring in d orbitals into the process. Okay, so I already know carbon and hydrogen. Oxygen, 1, 2, skip the middle, 3, 4, 5, 6. It has 6 valence electrons. So I'm going to start out with oxygen. 2, 3, 4, 5, 6. So I went around and then I went back again, filling in pairs. Now, to be clear, that is a legitimate one. Having the unpaired electrons opposite each other would also be legitimate. This is really a 3-dimensional shape. These are really tetrahedrons. And we're actually going to see shortly where it's going to turn into a triangle. Okay, let's do the hydrogen. It has the electron, and we already did the carbon with its 4 valence electrons. Okay, so why do I keep putting the pen down? I need a pen. I'm going to draw my carbon. Typically, the first element is in the middle. It's the least electronegative. The one that's closest to being a metal is typically the one in the middle. Okay, so I have 4 electrons. I'm going to start pairing them off. I'll put the hydrogen. I'll put the oxygen. I'll put the hydrogen, and I'm left with a problem. I have an unpaired electron on the carbon and an unpaired electron on the oxygen. So I'm actually going to redraw this so that I can pair these both up together. I can make up to 3 pairs between 2 atoms. There are scenarios where you get 4, but you're getting into some more interesting scenarios that we're not going to deal with. And those are usually very unstable, to say the least. So I'm going to redraw this. And I'm going to turn my oxygen on its side. That way, those two now make a pair nicely. And then I'm going to clean this up because this is just kind of a mess. I have a double bond, which is what that is referred to as, and that is a double bond to oxygen. Okay, and thus I have my answer. So next up, I'd like to throw a couple more interesting curves at this one. And let's go for a molecule that I would prefer never to work with, although I actually have worked with this one in tiny, tiny amounts. It is, interestingly enough, in lima beans. Not in very large quantities, but if you eat an insane amount of lima beans, they can be slightly problematic. This is hydrogen cyanide. Okay, so let's go through the molecule here. I have hydrogen. I already know what that looks like. I have a carbon. I've already done that one as well. And in this case, I'm going to do the nitrogen. For the nitrogen, once again, it's the same as the other ones. Okay, so there's my symbol for nitrogen. So now, remember how I said typically the first one is in the center? Now, hydrogen only can make one bond. It only has one electron. Can it be in the center? No. So hydrogen will quite often come off in front. This is usually seen with acids, so ones that are able to donate a proton. And well, it's usually put in front because it acts very much like a cation sometimes. So it can't be the center. So we're going to go with the carbon, which is the next one on the list. So I'm going to do the carbon. I've got 4 electrons. I can put my hydrogen on one. I can put my nitrogen on the other. I am strategically writing it slightly awkwardly for a reason. Oh, look, I have, make sure the camera can see it. I have 2 sets of unpaired electrons. Okay, I'm going to go ahead and do that. I'm going to pair them up. So now I have H, Cn, and an unpaired electron. Okay, now let's look at a couple other examples. And actually I'll take a little bit of a running jump with this one because HCN quite often does lose that hydrogen. So quite often you get Cn minus, which is cyanide. So in this case, I have 3 Lewis symbols still. You're like, wait, no, it's 2. No, it's 3. So let's start out with, I've got the carbon like I did beforehand. It's the same as there. And then I've got the nitrogen, and it's the same as before. But then I have the minus sign. Remember, the minus sign means you have a surplus electron. So I have a surplus electron. Yay! So now, when I put it together, it's going to be a slightly different story. I have carbon. I have nitrogen. I can form a triple bond, and that electron is going to go over there. So now I have C, N, and typically we will put the things in brackets and put a minus sign. There, cyanide. Of course, if you can have anions, you can have cations. So let's look at a cation. I do apologize, there's a gnat, it's dreadfully annoying. Okay, so let's go for ammonium. This is a polyatomic cation. And so in this case, I have the nitrogen again. Nitrogen is the one that typically likes to do the whole cation thing. I have the hydrogen. And I get to remove an electron. And I can remove it really from any place that I need to. So let's go ahead and do this. So I have the nitrogen. That's going to pair up with the hydrogen. It's It's going to pair up with another hydrogen. It's going to pair up with another hydrogen, but I've got a problem. This is ammonia. This is not ammonium, because I still have a hydrogen I have to cram on there somewhere. So what I'm going to do is I will use my get rid of an electron, and I'm going to use it on that one, and now I can pair those two electrons together. So now I get this guy, and I can clean him up to this. Okay. So yeah, we have ourselves some Lewis structures. Typically this is a little bit more advanced. There is one more I want to show you, which is definitely a little bit more advanced than I usually deal with in survey. And for that I will need a fresh piece of paper. So let's make sure I actually get it on the table. Let's take a look at sulfuric acid. That is going to be H2SO4. So, this is going to be interesting. So when I look at this one, I'm going to start doing this kind of off on the draft, and then I'm going to go like, wait a minute, I need to modify things. So hydrogen, I know hydrogen's symbol, we've been using it a lot. We've used oxygen before, so that's going to be this guy. Sulfur, if I look at sulfur, it's going to be right below oxygen, so it'll have the same Lewis symbol as oxygen. Spoilers, it won't, but we will find out that we need to adjust things here in a second. Okay, so now I'm going to take these guys and I'm going to put sulfur in the middle because I can't put hydrogen in the middle. So I can put the sulfur in the middle. Now, when I'm making these bonds, one thing I have to keep in mind is that very rarely things will form rings or bond same atom to same atom unless they're carbon. Carbon has no problems doing that. Most other atoms don't. So I'm not going to do that unless I know for sure that's going to take place. And I know that that's not going to take place here. So I'm going to put my oxygen on. I'm going to put my oxygen on because if I put a hydrogen on, then I'm done. Notice how I switched the Lewis symbol from the oxygen. Instead of using this, I used that. Just same thing. Okay, I can put another oxygen down here. And I can put my hydrogens on my oxygens. And I still have two oxygens left over. Okay, so if I grab my periodic table and I look at it, I have the first row that only has s orbitals in its valence shell. The second row has s and p orbitals in its valence shell. The third row has s, p, and d orbitals in its valence shell. But as kind of the weird quirk of how the d orbitals are oriented, they're not generally invoked. However, they can occasionally be utilized in the valence shell. They won't be utilized if the atom is all by itself. They will be completely empty if the atom is just floating around in space. But when it forms a compound, sometimes they do form a part of the Lewis symbol. They become part of the structure. So in this case, I'm going to redraw sulfur's Lewis symbol. This is not wrong, it's just not what it's using. So I'm going to take the sulfur, and then I am going to draw its Lewis symbol with two d orbitals incorporated. So it's no longer a square, it is now a hexagon. And now, with it being a hexagon, I have 6 valence shell electrons, and there are 6 orbitals to put them in, an s, 3 p's, and 2 d's. So I can now use this guy in my new structure. I have sulfur, 1, 2, 3, 4, 5, 6. I know, always looks a little weird when you don't put the actual dots on there. You know, the invisible line. Okay, so now I can take an oxygen. I can put an oxygen there. And I can stick a hydrogen off of it. just like I did last time. Now, each oxygen needs to bond to two spots, so I can put an oxygen there, making those two a double bond. Put an oxygen there, and those are now double bond. That's a mess. That needs to be cleaned up. So now what I do is I get and if I want to be really fancy and clean it up a lot of times we don't actually sew the bond to hydrogen. And I don't know why, but this is kind of the cleanest looking one. Sometimes we'll clean it up and make it look like that. But that's purely aesthetics. Once you're at kind of this stage, you've got it. Okay, so yeah, not usually a curveball I throw at survey students, at least not a lot, but be forewarned. It's not off the table, it's just unlikely. So yeah, that is a few Lewis structures. And with that said, have a wonderful day.